Here we are studying the control characteristics of few power devices. So you can control characteristic means how to turn on the device and how to turn off the device. So for any devices there is a one control to turn on the device and there is a to turn off the device. For an example, SCR, which terminal is used to turn on the SCR and turn on the SCR? Gate is used to turn on the SCR. So for similarly for a MOSFETs, which terminal is used to turn on the SCR? Gate is used. For transistor, which terminal is used to turn on base? So similarly, so here we are studying how to turn on the devices and how to turn off. That is also very important in few circuits, few devices. For an example, in an SCR is having three terminals: anode, cathode and gate. Here this is load, okay. So here we are applying the input and it is transferred to load. It is transferred to load through this SCR, okay. For that we need to turn on the SCR, okay. To turn on the SCR we have gate terminal and we need to apply a gate voltage like this. We have studied that a short pulse is enough to turn on the SCR. If you apply a gate voltage like this, here I am considering I have connected a DC input in the source side. DC source I have used, okay. You are aware of that DC source is taking a say constant value for all values of t. You assume that here there is a DC source, it is taking a value of Vs, some constant value, I am saying that Vs, and for all values of t, so it is constant, and I am applying a short gate pulse like this to gate terminal of an SCR in between gate and cathode. So what happens? SCR turns on. During the, if you measure the load voltage, we are measuring the load voltage across this load, across this load, across this load. So if you are measuring a load voltage here in between these two, so we are getting a load voltage like this. Because SCR is in on, so whatever input we are applied, it comes to load. So here input is DC, so till you turn, we have turned on somewhere here, that's the reason this is my load voltage. Load voltage is constant, load voltage is constant, and we are getting a load voltage. Its magnitude is ideally Vs. Strictly speaking, if you are applying a Vs, the drop of the SCR we need to deduct from Vs, then remaining value comes to here, load, okay. Then one more thing we need to understand here we are applying a gate pulse for a very short duration. Yeah, I agree, the SCR will turn on here, SCR will turn on. The next question arises here, we are changing the gate voltage from some high value to low, like from 3 volts to 0. So what about SCR condition, whether SCR will remain in on or SCR will change to off? SCR will remain in on, because we have studied that once SCR has already turned on, so if the current which is flowing in an SCR is more than the holding current, SCR remains in on state. SCR, even if you remove the gate voltage, we have removed the gate voltage here, okay, because we have made the gate voltage as 0. So then then you can ask questions when it will turn off. If by chance the current which is flowing through an SCR is coming below the holding current, then SCR will turn off. Until that, or until current comes down below the holding current, SCR remains in on state even if you remove the gate pulse. Okay, that's a reason the output voltage continues, means output here load will receive the input voltage. Okay, whatever input we are applied, the load will continue to receive. Okay, so because SCR remains in on state, okay, that's the reasons we have plotted the output voltage as same as input. Next question, so during that instant one more voltage if I apply, nothing will happen, SCR will remain on. Then if you apply negative gate voltage, strictly speaking we should not apply negative gate voltage. Okay, so this better you remove it, so this part you no need to show it. Okay, so then assume that if you are applying one more pulse, same thing continues. So then you should ask a question, sir, is it possible to turn off the SCR using gate terminal? No, not at all. So summary of this is, we are using the gate terminal of an SCR just to turn on the SCR. To turn off the SCR, we should make some other arrangement such that arrangement should reduce the current which is flowing through an SCR to below the holding current. So that is a different part, that is we call as a commutation circuits. Here in an SCR, a separate commutation circuitry is required to turn off an SCR, and it is not possible to turn off an SCR using gate terminal. Okay, next we will study some other circuits like GTO, gate gate turn off thyristor. Here I said it is not possible to turn off a thyristor using a gate terminal. So that disadvantages is rectified here, in the sense that disadvantage is removed here. In the sense, here one advantage of this GTO is, if you want to turn on this GTO, you just apply a gate voltage like this, and if you are applying an input like this, if this is an input you are applied here, if this is an input you are applied here, that same input passes through this GTO and goes to load. So load will receive that input. Here also very short pulse is enough, no requirement of continuous gate voltage. Okay, then next questions, how to turn off this GTO? You just apply a negative gate voltage, then this GTO will turn off. If it is turned off, it is acting like an open switch, so no connection between load and source. So load is detached from the source. So load is not receiving the current, or load is not receiving the voltage. So what is the load voltage? Load voltage is 0 until once again you turn on the GTO. How to turn on the GTO? GTO we can turn on by applying a positive voltage. Next. So this is a control characteristic of GTO. Next, there is one more circuits like SITH. It is almost same as GTO. So where we can apply positive voltage to turn on a SITH, and we are applying a negative voltage to turn off the SITH. The control characteristics of SITH and GTO is almost same. Next, we can use power transistor as a switch in our power electronics. So what are the three terminals of the power transistors or collector, emitter and base. We knew that whenever VB is more than 0.7, then only base emitter is forward biased. So which is a terminal, which is base emitter is a terminal which is used to control a transistor. So if base emitter is not forward biased, transistor cannot enter into on state. So we have studied that IB is a control, IB base current is a control variable. In the sense, if IB is 0, the current which is flowing IC is also 0. You have studied very well, IC is equal to beta into IB. IB itself is 0, there is no chance of IC. So consider this is a base terminal and this is emitter. If you similarly we require some pulse here or some voltage sources VBE to turn on an transistor. Here I am using this transistor as a switch. So why we switch, controlled switch? In the sense this is an input power and this is load. Our aim is to transfer this power to load only when I turn on this switch. How can I switch? How can I turn on this switch? By applying VBE, base emitter voltage. Base emitter voltage we should apply to turn on. Okay, one important characteristic is here is, okay, we have applied VBE, then this will turn on. If you want to retain this transistor in on state for a duration, for this much duration, for that much duration we should keep VBE, this applied voltage we should keep it. Means if you are applying some points more, some 1 volts, I should keep that 1 volts till here. By chance if you make VBE 0 somewhere here, what happens? This transistor will change to off. So for how long you want to keep this transistor in on state, for that much duration we should keep VBE more than 0.7 or else the required, okay, depending on your circuits. Next, now if you are making VBE 0 here, then what happens? This transistor will turn off. This transistor will turn off. Once it is acting, it is turned off, it is acting like an open switch, so no current flows from input to power, so no voltage across the load. So that's the reasons load voltage is 0. Next, MOSFETs. In a MOSFETs, we have studied that drain and source, it is passing the it comes in a path of a current, and which is a control terminal, gate is a control terminal. So for an example, enhancement mode MOSFETs, if you apply positive voltage in between gate and source, a inversion layer or else, correct, minority carriers are concentrated below the in between drain and source. I think you have studied that in MOSFET enhancement characteristics. So an layer is created, channel is created in between drain and source in the presence of gate source voltage. If you remove that gate source voltage, the channel is not created, so there is no connection in between drain and source. So here also we are considering that we are applying an input voltage like this, we are applying an input voltage like this. So this input voltage travels or reaches to load only when this MOSFET is in on state. To turn on the MOSFET, we should apply gate source voltage. Gate source voltage, when we apply like this, when we are applying a sufficient gate source voltage like this, this MOSFET will turn on so it will passes the input voltage to load. So if you are measuring a voltage across load, the load is receiving power like this. How long? Until you apply the gate source voltage. By chance, if you are removing the gate changing the gate source voltage to 0 like this, so the channel whichever is already appeared in between drain and source will disappear here onwards, and there is no path for a current to flow from drain to source. So it is acting like an open switch. So no current will come from input to load. So load voltage is 0. So load is detached from the source. Here also, to keep MOSFETs in on state, we should retain this gate source voltage from here to here. If you want to turn off the MOSFETs, you just remove the gate source voltage, or else you can make gate source voltage 0. There is another power electronics switch. I have not shown here, but you can consider it as IGBT. IGBT. This is also one important IGBT. One important power electronic switch. It is invented by a person like Baliga. So he is an Indian scientist, Indian based scientist. When he was in General Electricals, he invented IGBT. This IGBT is almost same as MOSFETs. In IGBT, the two characteristics of transistor and MOSFETs are used. I will tell you one thing. The switching loss of the transistor is high compared to MOSFETs. Then the on-state loss of the transistor is high compared to MOSFETs. Switching loss of the transistor is high compared to MOSFET. On-state loss of the MOSFET is high compared to transistor. So he has mixed the good characteristics of transistor and MOSFETs, and he has made a new device called as an IGBT, where the IGBT's switching speed is better than transistor and on-state loss is better than MOSFETs. Okay, so it is having a moderate switching losses and moderate on-state losses. The IGBT is extensively used in power electronics. It is having a terminals like gate and collector and emitter, but there also collector and emitter there also. So the IGBT is shown like this symbol. This is gate, this is collector, and this is emitter. In place of this MOSFETs, you can connect here. So there we are applying a gate voltage to gate and emitter, and in the current path we are connecting using collector emitter. So here the both symbols, the symbol of transistor and as well as symbol of MOSFET, some part of the symbol of MOSFETs are used here. Okay, and the characteristic is also done in the same way, in the sense IGBT is having the characteristic of transistor and as well as few characteristics of MOSFETs. So in IGBT also, if you want to apply a gate, if you want to turn on the IGBT, we should apply voltage to gate emitter, and if you want to turn off IGBT, we need to remove the gate emitter voltage. If you are using an IGBT, you call this control signal as VGE, because in IGBT collector and emitter is there. Okay. Thank you.